Hi everyone, my name is Shayan. Today I want to present a paper which is called Scene Representation Networks or Continuous 3D Structure-Aware Neural Scene Representations. Learning a scene representation has always been an important problem in computer vision, and a variety of models have been used so far, which includes those with 3D inductive biases like voxels or meshes, or those unaware of that like simple latent variable models. With the rich scene representation at hand, we can apply it to other downstream tasks such as robotic manipulation or navigation, where a robot interacts with objects in its surrounding or moves around in an environment. In terms of contributions, this paper has proposed a novel continuous 3D structure-aware scene representation capable of encoding information about both geometry and appearance in a multi-view consistent manner. This representation is learned end-to-end along with a differentiable renderer based on ray marching without any 3D supervision of geometry. This model is also generalizable to other scenes with different geometry or appearances. Finally, it is evaluated on novel view synthesis and few-shot reconstruction. Let's start with a simple setting for the problem formulation, where we are given a set of images, each of which shows how an object looks from a different viewpoint. In addition to that, all the necessary information about the viewpoint is provided in camera pose and intrinsics. Next, we have an implicitly defined scene function which basically takes in a point in 3D space and uses an MLP to map it to a feature representation V of dimension n. We hope that this modeling captures different levels of information such as visual information like surface color or reflectance, or geometrical features like shape or sign distance to closest surface. As this function accepts any point in 3D space, it provides a continuous representation. That's why we can easily sample at arbitrary high resolution from the function to capture fine-grained details. But in practice, the limited capacity of MLP used for parameterizing this function is a constraint. Next, we have a differentiable renderer that maps an implicitly defined scene function to an image based on the viewpoint. To render a scene, two steps are taken. Firstly, we do ray marching, and secondly, generate color values for each pixel. Based on the principles developed in project geometry, as a function of distance from camera, we can easily parameterize the ray that starts from camera center, passes through pixel U and V, and marches out through the scene. To find the intersection of this ray with objects in the scene, we initially start from a point close to the camera. Then at each step, the feature representation of the current estimate is retrieved. Since this provides helpful information about the geometry, it is then passed to an LSTM for further processing and predicting the step length as output. Finally, with that step size, we move to a new estimate, and this whole procedure is iteratively done for a fixed number of steps, and the hope is that at the end we reach to the true intersection points. Because at the beginning of the training all the model is initialized at random, it is so likely that a dynamic termination of the for loop doesn't give back a good estimate of the intersection point. Anyway, after finding intersection points for all pixels, once again they are passed to the scene function to get back their feature representations. As these features may encode visual information as well, another MLP is used in order to map each of them to RGB values. As this generation operates on pixels independently and always maps the same 3D coordinate to the same color, rendering remains consistent from multiple views. All I've presented so far is not yet generalizable to new scenes. Next, we see how the model is extended further to accommodate new scenes. Assume that we have gathered some observations of multiple instances of class of objects like cars. Suppose that each instance has its own implicit function. Also, all these functions are presented as MLP functions sharing the same structure but with different weights, so they all coming from an L-dimensional space. As they all parameterize scene function of instances in same class, they reasonably live in a lower dimensional submanifold of size k, showing intrinsic dimension of this space. This latent space is itself parameterized with the latent code scene Z. Given this code, we can regress the weights of the scene function MLPs with another MLP called hypernetwork. The latent codes are also free parameters learned individually for each scene. So to find the optimal model, we minimize a loss function with respect to model parameters, which includes those for neural renderer, hypernetwork, and latent scene codes. The loss function is simply summation through all instances and then for each instance through all of its observations. The loss function is composed of three terms. First term uses an L2 loss to penalize the difference between the input image with its re-rendering version. Second term enforces the ray marching algorithm to have a positive final depth. And the third term imposes a Gaussian prior with zero mean and diagonal covariance over latent codes. To optimize in few-shot setting, the assumption is that both hypernetwork and neural renderer are trained faithfully. And with regard to just few given observation of a new instance, we find the optimal latent using the same objective as before. Now let's have a brief overview over results and discuss them. First experiment is done over Shepard-Metzler datasets that consists of objects, each of which with 7 cubic elements placed in different configurations. Qualitative comparison here between SRN and the baseline DGQN in novel view synthesis of objects shows that the SRN performs much better in terms of having more coherent and less blurry renderings of multiple viewpoints. Next, the model is examined on cars and chairs of the well-known ShapeNet dataset. Trained models are assessed on novel view synthesis of objects in training sets and test set as well, but with the difference that for objects in the test set, only 1 or 2 observations are provided. Quantitative results in the tables show superior performance of proposed model compared to baselines with a significant gap, even in the two-shot setting. Outperforming is also evident in these qualitative results. For example, for the brown chair here, the SRN is able to render the front handle, which is not the case for the other two baselines. Here are also the results illustrating that the interpolated latent codes correspond to meaningful objects and we can smoothly transit from one object to another. With the persistent feature representation and independent pixel generation, the render is naturally generalizable to camera poses not seen during training. Empirically, this is also shown in right and left animations where the camera is transformed to irregular poses not seen during training. In this basal face experiment, we have meaningful latent code disentangled into identity and expression. On the left animation with fixed identity, changing expression code non-rigidly deforms the face. On the right, interpolation between different identities and expressions produce a smooth transition. This work, like any other work, has its own limitations. Firstly, in this model, it is required to have access to extrinsic and intrinsic of camera. However, they're not provided in many real scenarios. Also, SRN does not incorporate view or lighting dependent effects, but in real world they strongly affect scene rendering from different viewpoints. Also, SRN experiences failures when the ray marching gets stuck in holes of surfaces or passes closely by occluders, and this is also demonstrated in the chair case here. Also, the latent space seems not to generalize well to new objects coming from a different distribution, like in this car where the SRN does really bad in geometry and just matches the texture. Some architectural choices are also debatable. You can see that from the results, occasionally high-frequency details in texture were not learned so well, so that's bad. And however, in some recent work, use positional encoding or sinusoidal activation functions, which are proved to be helpful in obtaining fine-grained details. Also, hypernetwork is computationally expensive since it regresses parameters of another huge network. One may use recent meta-learning techniques like in MetaSDF to find a good initialization for weights for new scenes. Moreover, the ray marching is really time-consuming as it calls a forward pass of the scene MLP at each step. Now let's recap some of the contributions in this work. So without any 3D ground truth geometry, a 3D structure-aware scene representation along with a differentiable renderer is learned end-to-end to encode both geometry and appearance in a multi-view consistent manner. And the model is finally generalized to other scenes and ultimately evaluated on novel view synthesis and few-shot reconstruction.